So the start of the lecture today, we will just do a quick worked example of evaluating the Hessian and its eigenvalues and determining whether a global minimum exists. Then we finished the part of this last part of this module on establishing that a minimum exists. Now we're going on to the methods of determining it, and we'll encounter two methods. One's called gradient descent and the other is called conjugate gradient descent, and they're both related. And the method is in the title, helpfully. Basically, we're using the gradient, grad of f, to navigate from wherever we are in the function to the minimum. And this turns out to be an incredibly useful method in data science, in other areas as well, to determine a minimum of a multi-dimensional function. Okay, so let me just summarize where we are and where we're getting to. So optimization, we're on the topic of 2D optimization. And the first part is establishing that a minimum, in this case, exists in 2D. And then the main sort of tool for that ultimately is the Hessian matrix. And its eigenvalues. Okay, and establishing point, and we're going to just do an example of that to finish off that section. So this is what we've been doing the last few videos, is just establishing the minimum exists in the first place, and then obviously we want to determine the minimum. And this is the last two topics then of this term's work, which will be two methods. One's called gradient descent, and they're both related to one another, and conjugate gradient descent. Then we're done. Give yourself a firm pat on the back for getting through all this stuff. So let me finish off the Hessian stuff and with an example, and then we'll start the gradient descent. So that's where we're going. So we can do e.g. of Hessian and eigenvalues. So we consider quadratic function. Now I'm just going to reintroduce this notation I've done before. When we put a vector into a function, it really is equivalent to saying that if that is a 2D vector, say that has components x and y, is a function of x and y. It's just a very compact way of doing it. And of course, if you've got many dimensions, you want to just put the vector in, not all the dimensions. So you could do f of x and y. So our vector in this case is just x, y, right? Okay, that's all it is. And 3x squared plus root 8xy plus 2y squared plus 4x plus 3y minus 5. Okay. So what we want to do is calculate the derivatives of this, and then put it into the function, into the Hessian. So the Hessian is, remember, I'm going to use shorthand here now for the second derivative. Second derivative with respect to x on there, second derivative with respect to y there, and then the cross derivatives, which whenever it's continuous and differentiable is going to be the same, but we put in anyway for completeness. And we just fill in these. So the second derivative, although you've got many terms here, when we do the second derivative with x, it's only the 3x squared term that's going to lead to anything, because all these other ones are going to go to 0, right? That one with two derivatives with respect to x is going to be 0, and the others are 2. So that then leads to 6. Okay, first derivative is 6x, second derivative is just 6. And the second derivative with respect to y equally is only due to this y squared term, so that gives us 4. And the cross derivative is actually only due to this term here, this xy term. So that's just going to give you root 8. And lo and behold, we've got Hessian. You always, it's pretty much in all these examples, it's symmetric, and most examples of the Hessian are constants because of the way the function is. Now in the lecture, if you're interested in Hessian sort of function of space, there's an example in the lecture notes that you can look at, 5.4.2, but I'm not going to dwell on that as that's not the core stuff for this year. So normally they're constants and off diagonal. So that's our Hessian, and then we just simply need to find the eigenvalues of this thing. So let's just write it out again. And eigenvalues of the 2 by 2 matrix is simple. So I hope you've seen again. We've had some, these things like quadratic forms, Hessians, positive definiteness. They're new concepts, maybe seem a little bit abstract, but once you get a problem where you've got a 2 by 2 matrix again, we're back into sort of our comfort zone, shall we say, and we can sort of compute things and then start to understand it sort of more from that perspective. So we compute our eigenvalues with our determinant then so this is a determinant, so that's essentially taking the lambda off the leading diagonal and then root 8, and then the determinant is just multiplying through the diagonal, taking off the off diagonal. We end up with let's do each of this. We have 24 minus 10 lambda plus lambda squared. So that equals 0, by the way. And it's minus 8 equals 0, which implies that lambda squared plus 10 lambda plus 16 is 0. And I've made this easy with factorizable. So we've got lambda minus 8 lambda minus 2 equals 0. So lambda equals 8, 2. Okay, that's a very standard calculation on this page, really, that you would have known before this module, and that's good. So lambda equals 2, 8, i.e. h is positive definite, as all the lambdas are greater than 0, and thus f is convex and has a global minimum. And that's all there is to it once you've got your Hessian. So compute the Hessian, the eigenvalues. So and there's more of these examples out there in exam questions and courseworks and tutorials. So and that's what I say a lot about this, the new concepts in this module. I often try and distill them down to a simple, I say, a 2x2 problem, matrix problem that we're very comfortable with. Partly to show you that although it seems a little bit, all these new concepts, actually they can be anchored in quite a very doable example. And we'll carry on using that tool as we go forward. Right, so that's establishing that the minimum exists, but now how do we calculate the global minimum? So here's a start in what's going to be, so this, just going to use slides for a minute because I've got a few so we're going to start with, and let me write on the top, something's called gradient descent. And this is another, as you say, there's two types of names for numerical methods. There's the ones that are named after the people who invented them, which is great for the people who invented them. They get them famous, whether you're Jacobi or Gauss-Seidel, Gauss and Seidel. The problem is it doesn't tell us how the method works. Whereas other ones like gradient descent in this example, golden section search, have a lot of the method in the name, and that's very useful. And the key idea here is that we've got the gradient. We're going to use the gradient, so we're going to use grad f. Okay, so your function at any point in x and y, you can calculate grad f, and if you calculate minus grad f, that is the descent direction. Okay, so this is a very simple example here. We've got a surface plus x squared plus y squared. It's trivial actually where the minimum is, right? I've done that on purpose. It's x is y comes 0. That's really that's your minimum. But what we're just going to use this example. So I've plotted the with a sort of a surface plot here of the function, and the colors as they get more yellow, it shows it increases function. But just show you the example. So essentially it's a parabola in both directions, x squared plus y squared. So it's completely symmetric as you rotate round. So it's the simplest thing you can think of just to illustrate what's going on. And then I've constructed the direction here. This was done in MATLAB. Just calculate what minus grad f is. So grad f in this case is a vector, which is so minus grad f is minus 2x, yeah, minus 2y, because grad of f is 2x 2y minus grad f. So I've just calculated, so for any point x, y, so starting from this point, strat, start, and minus grad f in this case is down here, and it's basically pointing straight to the minimum. Okay, but you get the idea. This is the idea, is that if we've only got local information about the function minus grad f, we can navigate towards the surface. So the 2D optimization methods we're going to consider all involve the gradient. The conjugate gradient will be a modification. It'll become apparent when we get there how that one works, but they're both related. In its essence, it's about starting with the gradient, constructing the minus the gradient, and steering us way down to the minimum. And this very simple example where we know exactly the minimum hopefully just fixes this sort of picture in your mind of where we're going. Okay, and I'm going to write down the method in a minute. Okay, so that's probably the simplest example, is a bowl function. So that's something that's in the lecture notes, just taken straight from the lecture notes. And here's another example, a less symmetric example. But then here again, when we construct, so again the minimum is still at 0,0, but the function is elliptical now. It's got 4x squared plus y squared. So again, we're going to, but we're going to still use gradient. And you probably start to see that actually this time, with this example, we're not going straight to the minimum. So we're going to have to do a series of steps to navigate in. Okay, so okay, so that's where we're going. Okay, so let's get going with that. So, gradient descent, sometimes also called steepest descent. We're going to use minus grad f, which is from vector, your vector calculus, and also from your first year calculus, is the fastest descent direction. So I'm not going to derive it here, but you will do it in vector calculus, and also you will do it, you have done aspects of it in first year calculus, that your minus grad f defines the fastest descent. It makes sense, doesn't it? Because it's, you know, in a way, grad f points up the hill, the most fastest direction up the hill. Minus grad f points down the hill, most fastest direction down the descent. And it has different steps. So we have a trajectory, step, and we have a minimization along the trajectory. This is a key thing. We're going to just define a trajectory using minus grad f. Well, we've seen a bit of that. Then we do a minimization along the trajectory. So basically, the grad f, minus grad f, is going to define a section, if you like, along your 2D function in 2D. And we're going to have a start and end of each step. And then, but the question is how far along do we go along that trajectory? Well, that's where the minimization comes in. So we basically find the minimum of the function along this trajectory, and then we stop, and then we repeat. And that's the idea. So it's probably the second step computationally. It takes a little bit of time to get used to, maybe, but you can see the idea. So it's going to be a series of sections along the function. It's a series of steps. But let me just write down those steps, and that'll probably be time to finish then. So the trajectory is going to be like this. So we're going to have our vector, a position vector, is going to have, so lambda, by the way, is no longer eigenvalues. Lambda is trajectory length. So this is a little bit of, we've just been using lambda for eigenvalues. Now we're using it for trajectory length, because that's the way this notation works. We're going to change to alpha fairly soon anyway, but let's stick with this notation. So we've got this lambda n now is a trajectory length, and we multiply our gradient times the trajectory length along. So we've defined, if you like, we've defined the direction of the trajectory here. We've got x of n, xn plus 1, but we haven't determined yet at this stage of the algorithm, so n is just our step of our algorithm, what the length is. That's where the next step comes in, which is minimize along trajectory. So let me just, draw out. This is very common in the optimization stuff. I just draw some contours of the function, and the minimum is going to be there. So say now if xn starts there, and we've got xn plus 1 here, and we haven't determined the length, you can see that we have a, if you like, a section of your 2D function along the trajectory. So what you observe, actually what we've done is by defining this trajectory with minus grad, and if you just look at little values, that actually forms a one-dimensional function from this bigger 2D function along this trajectory. So you're basically minimizing this function along here. So basically it's trying to find the minimum along the trajectory, and then it's going to stop, and then it's going to repeat. Yeah. So let's write that down, what that minimization means. And it's basically, you have, so lambda n is trajectory length at step n. F of x of n plus 1 is the function value at the end of the trajectory. Remember, we're starting off at xn here, and then we're going to xn plus 1. So we just apply a calculus, and we minimize with respect to this trajectory length. So we do d by d lambda n, and remember we can put vectors into functions which satisfy with that. F of x of n plus 1, it becomes very useful, equals 0. Okay, so there's a lot in this expression, and we're at the end of this video. Make sure you understand each little, and it's written out neatly. It's equation 5.6 in the lecture notes. Understand what's going on here. So it's quite complicated because you're evaluating a function along a trajectory. It's something you kind of done maybe a bit in first year calculus. You will do in second in vector calculus. I appreciate that's next term. But it's basically defining a trajectory, xn, and evaluating the function just along there, and then minimizing with respect to lambda. And that's the key. And once you've got that, then you can repeat. And the idea then, as you go forward with gradient descent, let me just show you examples. As you do one trajectory, then you do another one, and another one. It turns out it's getting smaller and smaller. It will do, and it will eventually converge towards the minimum in this way. Okay, and that's how it works. So that's sort of the general way of writing it down. Now we want a method that we can compute by hand, and then I'm going to set that up next time.